Okay, it's exactly 3 o'clock, so I'm gonna get started. Hi, everyone. I'm Sam. Yeah, feel free to holler back when I say stuff. Hi, everyone. Hey, I'm Sam. We're gonna talk about progressive web apps, their past, their present, and their future. We're gonna start all the way back at a new internet. The first working draft of HTML5, then known as Web Applications 1.0, was released on September 1st, 2005. For context, that was almost 18 months before the iPhone was released, over 3 years before Android was released, and over 4 years before the terms mobile first and responsive web design were coined. Before all of that, there was this draft, this thought of what the web could be. The first sentence of its abstract sums up its intentions really well. This specification introduces features to HTML and the DOM that ease the authoring of web-based applications. Applications. That was what the version of HTML5 was about. That vision put forth September 1st, 2005, that the web could and should be a place for applications, not just documents. This was a powerful thought and a vision we're still trying to fulfill today. But this was 2005. In a few short years, the world the web lived in was going to change drastically. A true paradigm shift, if ever there was one, moving from desktop to mobile was about to happen. But this idea that the web could be a place for applications proved strong enough to withstand the shifting sands of computing. Even more than that, it would show the need for the web to make this shift. But that's getting ahead of the story. The web, up until the introduction of HTML5, was designed to be used online, a series of connected documents. Web applications, as a major driving factor of HTML5, then became the need for web applications to work offline. In May of 2007, Google introduced an open source browser extension called Google Gears, designed to help make web applications work offline. The quote's a little small on my text. One of the most frequently requested features from Google's web applications is the ability to use them offline. Unfortunately, today's web browsers lack some features, fundamental building blocks necessary to make applications work offline a reality. In other words, we found the need to add a few new gears to the web machinery before we could make our apps work offline. While not a web standard itself, it was built on top of web standards, adding, quote, just enough AJAX to make current web applications work offline, with the goal of evolving it into a set of web standards. Gears include a number of components that may sound familiar to you today. An SQLite-powered database, a local server that could cache and serve resources, and a way to create desktop shortcuts. While Gears would officially be deprecated in March of 2011 in favor of web standards that had finally caught up, its influence is going to be hard to miss. The earliest draft of the HTML spec that I can find that mentions offline web applications comes from October of 2007. A subsequent draft sums up the capabilities that HTML5 provides to help applications work offline. It is client-side SQL, online and offline events, local storage, and finally, quote, offline application caching API, later known as application caching or simply app cache. App cache was a big deal. For the first time, there was a standards-based way of telling a web browser that certain assets, your CSS, your images, your HTML, should be made available to a user when they're offline. App cache was entirely declarative. You created a cache manifest, put the specific files you wanted the browser to cache, and it, through a series of rules, would. The first two browsers that would get app cache support would be Safari 4 and Firefox 3.5, both released June of 2009. Android browser 2.1 would get it a year later, and then Chrome 4 and Safari on iOS would get it in early 2010. It wouldn't land in Opera until mid-2011 or in Explorer until the end of 2012. App cache was great in theory, but in practice, it had a lot of gotchas. Jake Archibald described why it was so hard to work with it in his A List Apart article, Application Cache is a Douchebag. A few key, real painful ones mentioned in the article include files cached with app cache would always come from the cache, even if the user was online. The app cache would only update if the content of the manifest file had changed, not if the content of the things being cached had changed. And non-cached resources wouldn't load on cached pages, even when online, by design. Replacing app cache was the start of a new chapter towards what we know as PWAs. But before we get there, we need to take a detour into what web apps looked like at desktops at the time. From conversations with members of the Chrome team who were there at the time, what we know today as progressive web apps started life back in 2010. At the time, there are two competing schools of thought for how to make the web a better place for applications. One school of thought was to work with the standards process and improve the core platform. The other school of thought was that the standards process wasn't fast enough for features they wanted to deliver. The group that wanted to work on the standards process, led by Alex Russell, Dmitry Glaskov, and Alex Komorowski, went on to propose and help drive standards, including mutation absorbers, HTML templates, object observe, web components, ES modules, ES classes, CSS variables, and web animations, just to name a few. The group that wanted to work faster than the platform created Chrome apps. Launched December of 2010, Chrome apps' goal is something you've likely heard from any number of similar solutions, from Electron to Cordova to even progressive web apps today. Build fully featured applications that just happen to be built with web technology. Packaged Chrome apps may sound familiar to you PWA developers out there. They could be launched from outside of Chrome, got their own app windows, and could potentially or generally behave like other apps. They were offline by default. Resources required to run offline came with the app, and it included APIs to make pages resilient under poor network conditions. New APIs were added to get low-level hardware access. For instance, USB and Bluetooth, and new shared data APIs to let you more easily interoperate with other applications on the system. Chrome apps also introduced native client, or NACL, and siblings, showing web apps or allowing web apps to run C and C++ code in the browser, while allowing migration path to existing code bases for better performance than could be achieved with JavaScript alone. What these two teams learned and developed during this time would become indispensable as people took another pass at getting web apps to work offline. In August of 2012, a group of developers and browser vendors came together to talk about app cache, first in London, hosted by FT Labs, and then in Mountain View, hosted by Mozilla. The goal, talk about practical experiences with sites that they were developing today. Facebook, Gmail, the Financial Times, and The Economist, Twitter, and Microsoft Outlook were among the participants. The conclusion? Not quite tear it all down, but pretty close. In June of 2013, the Extensible Web Manifesto was published. Remember that group I mentioned that wanted to improve the web standards process? One of their leads, Alex Russell, would help write the Extensible Web Manifesto. It solidified many of the lessons he learned in that previous work. The authors of the manifesto had seen that with high-level abstractions like app cache, users either needed to buy into the entire thing or replace it entirely with an alternative. They believe that users should be able to take control only at the point they needed to accomplish the goal they wanted. With this in mind, the manifest offers 4 design principles for an extensible web. Focus on adding new low-level capabilities that are secure and efficient. Expose low-level capabilities that explain existing features, allowing authors to understand and replicate them. Create a virtuous cycle between standards and developers by developing, describing, and testing new high-level features in JavaScript first, and then allowing developers to iterate on them before they become standardized. And finally, prioritize efforts that follow these recommendations and deprioritize those that don't. The first commits for what would become the service worker spec were laid down by Alex Russell in February of 2013. And by the time the first public working draft was published in May 8th of 2014, so the service worker spec was a shining example of the Extensible Web Manifesto at practice. Where app cache provided a high-level declarative syntax for caching and then had its own rules for deciding what to save, service workers and the cache storage API were low-level APIs that allowed users to script what should happen with JavaScript. Using both service workers and the cache storage API, users could describe and recreate how the browser handled caching and how app cache handled caching. Chrome 45, released September 2015, was the first browser to fully support both the cache storage API and service workers. Firefox 44 and Samsung Internet would get support in 2016, followed by Safari 11.1 and Microsoft Edge in 2018. By the end of 2020, some 13 years after it was first described, App Cache has officially been deprecated and removed from Chrome, Edge, Opera, and Firefox. Service workers and working offline is only one part of the progressive web app story. Getting onto the home screen required something else. When the iPhone originally launched in 2007, it didn't have the App Store. The original iPhone came with standard apps, Safari 3.1, and the ability to make special website bookmarks, known as web clips, which would add a website to the user's home screen. Then, on July 10th, 2008, over 2 months before Android was launched, Apple released the App Store and fundamentally changed how people think about software, how to buy it, what it should cost, and their relationship with it. As it turns out, software development was going, especially web development, was going through not one, but 2 paradigm shifts at once. The move from desktop to mobile, and the move from app discovery from search engines to app stores. The web, though, didn't have an app model at this point, in a time when all conversation was around apps. The result? Uncertainty that the web would survive these tectonic shifts happening. By the time the web had an answer, it had seemingly already lost. Building on the trends of multiple years of data, the ComScore 2015 mobile app report painted a stark picture of web usage on phones. Users spent just 13% of their time on mobile devices and browsers. The rest was in apps. Apps were eating the world. But apps are a tough business. While the majority of time was spent in apps, comparing the top 1,000 mobile properties versus the top 1,000 apps, the web had audiences 2.5 times larger and grew twice as fast. That said, while it was harder to build an app audience, app users spent 18 times more time in their apps than mobile web visitors did. Apps also seemed to be a zero-sum game. 4 out of 5 smartphone app minutes were spent in an individual's top 3 apps. Tablets, even more so. The big takeaways from the ComScore had from the data were, it's easier to build large audiences on the web quicker because of the web's superpower, linking. While mobile app usage was exploding, it wasn't at the expense of the mobile web or desktops. So they believed the key growth opportunity was in a multi-platform solution. Finally, app usage is an reflexive, habitual behavior where those occupying the best home screen real estate were used the most frequently. The web at this point had already more or less one desktop for most use cases, and it was already easier to build a larger audience faster on the web than apps. Linking and a single shared platform across mobile and desktop meant distribution of the web was much easier. What was the web's missing to stay competitive with mobile apps? Well, it lacked an app model. The 2015 ComScore mobile app report came at just the right time, as the pieces needed for a site to be added to a user's home screen were finally starting to fall into place. The missing piece in the app model came December 17, 2013, with the publication of the first working draft of the Manifest for Web Applications and Bookmarks. The spec, now known as the Web App Manifest, initially written by Marcos Caceres from Mozilla and Anisi Konstantin and Kenneth R. Christensen from Intel. It was designed to consolidate metadata about a web app, like name, icons, and URL to start when opened, from various meta tags into a single place. Its goal to enhance bookmarking capabilities and being able to add an web application to the home screen on a device. On mobile devices, Chrome would add support for adding web apps to the home screen in Chrome 39 November of 2014, followed by Samsung 4 in 2016, and Safari 11.3 in 2018. Between working offline and web app manifests, including key features like start URL and icons, the web now had an installation criteria for adding a website to the home screen. That criteria hasn't changed much since, but it didn't have a name. They were just installable web apps. And then on June 15th, 2015, Alex Russell and Francis Berriman would go on to coin the term progressive web apps to describe web apps that were reliable and could be installed on mobile apps, just like mobile apps. A normal website that, when built well and earns a place on your home screen, could progressively become an app. the name has stuck. Halfway through 2015, all of the pieces were in place for an app model for the web. It had service workers to allow a site to work offline or with limited connectivity. It had web app manifest to describe how to install and what should be and what its function should be. And it had a name, Progressive Web Apps. It was only a matter of time before one existed. The first PWA I can recall, and maybe the first one you can recall too, is the Air Horner, released by Paul Kinlan midway through 2015. While fun, it was mostly just a demo. Yes, it's just a button with an air horn. It's fabulous and it still works. Or maybe it was the Google I/O 2015 website, which was probably the first large-scale PWA and whose development motivated the creation of SW Precache and SW Toolkit, which would go on to become Workbox. But the world's first production PWA is generally considered to be Flipkart Lite by Indian e-commerce company Flipkart, released November 9th, 2015. Introducing their PWA had dramatic effect on their user engagement. A key metric for Flipkart was tracking data usage to complete the first transaction. When comparing Flipkart Lite to the mobile app, Flipkart Lite used 3 times less data. This was especially important as 63% of Flipkart Lite users were on a 2G network. Service workers and the low-level friction of the web's distribution model combined to make these possible. Getting Flipkart Lite onto the home screen was important too. 60% of all visits came from launching from the home screen, and those users converted 70% more than average users. Those two activities alone grew overall engagement 40% higher than it was before. Flipkart proved that PWAs can compete with mobile apps when installed, but e-commerce is a space the web was already good at. To be truly competitive, web apps need to be able to take on platform apps on their home turf. By design, the web is less capable than platform apps. Its drive-by nature makes exposing many APIs and features a security risk. But when the web is capable of delivering a particular experience, it can compete. Linking and the lack of gatekeepers to get your site online gives the web a better distribution model than app stores. A change to how PWAs get installed paved the way for closing this capabilities gap. The initial implementation of progressive web apps on Android was by design minimal. Basically, they were glorified home screen shortcuts. They didn't show up in the app drawer. They didn't show up in the app switcher. They didn't really feel like apps besides having a home screen icon. On Android, the base unit of administration for an application is called an APK, or Android Application Package. The APK is how Android apps deal with things like notifications and running in the background, targeting for sharing, backup and restore, and more. After the successful launch of Flipkart Lite and the momentum behind PWA started to build, the initial implementation's lack of integration needed to be fixed. On May 10th, 2016, the first CL for web APKs was merged into Chromium. Web APKs were a big deal for how progressive web apps would evolve. Dominic Eng, a leader for progressive web apps at Google at the time, shared that web APKs really built the foundation for the deep system integration we've been pursuing ever since. The deep system integration started life as Project Fizz. Project Fizz, named to complement Gin, an early codename for Chrome, had been around since 2014, not as a formal team, but as a collection of teams within Google, with the goals of bringing top requested APIs to the web, creating infrastructure that enables new capabilities to be experimented with and exposed in a risk-limiting way, and optionally enabling web apps to receive the same UI treatment as their integration with mobile and desktop apps. Fizz was responsible for a lot of early PWA work, including service workers, background sync, and push notifications, enabled with the availability of web APKs. They also introduced Web Bluetooth, first available in Chrome 56, and Web USB, first available in Chrome 61. The first 2 new powerful APIs designed to close that app gap. Project Fizz would evolve into Project Fugu and the current Capabilities Project, pretty much keeping the same mission and focusing on bringing new powerful APIs to the web. It would also move beyond Google to become a cross-company effort, including significant contributions from Microsoft and Intel. When progressive web apps were first launched, they were originally envisioned only for mobile devices as a way of helping the web compete with mobile apps. But the web is more than mobile. The benefits of PWAs extend to not just home screens, but to taskbars too. By allowing PWAs to be installed on desktop devices, the promise of write once, install everywhere could start to be fulfilled. Prior to PWAs coming to desktop, Chrome had something called bookmark apps. Built on the foundations laid by hosted Chrome apps, bookmark apps, so called because they were something between a bookmark and an app, were what was created when you added a site to your desktop. In 2018, when Chrome started work to bring true progressive web apps to desktops, the implementation was forked from bookmark apps. Rollout for desktop PWA started with Chrome OS version 67, released in May 2018. It would take another 3 releases to hit Windows and Linux, and then another 3 releases to hit Mac in 2019. Much like on mobile, desktop PWAs from the start proved that websites could earn their place on taskbars, often without much effort. At Google I/O 2019, Hulu shared their story of creating a desktop progressive web app to replace their legacy Windows desktop app that they had. Just like ComScore said in 2015, Hulu reiterated that even though their legacy app had poor reviews and lacked features, users still kept using it because it was ever present, just a single click away. They started small with a simple offline fallback service worker and a manifest file, just enough to make their replacement work offline and installable. It took one developer 2 weeks to build, QA, and release their new replacement. That was one sprint for their team, literally the fastest they could have delivered a feature. In the 3 months since launch, they saw 90% of their legacy app users adopt the new PWA, and compared to their website, saw a 27% increase in the return visits and a 5.5% increase in engagement. Desktop PWAs would come to Edge 79 in January 2020 and Safari on Mac September 2023. And that brings us to today. PWAs are here, can be installed on any device with a web browser, and there's lots of work going into making them even more capable, letting the web compete more and more with desktop and mobile apps. The Capabilities Project has launched almost 60 new APIs between Chromium 71 and 118, including expanded hardware support with WebHID, Web Serial and Web NFC, deeper OS integration with a file system API, a contact picker API, and web share target, and the ever expanding and even expanding what installed PWAs are capable of with the badging API, app shortcuts, and the file handler API. Web apps have become so capable that even Photoshop is now available on the web. Photoshop used WebAssembly to port their existing C++ code to the web, and added the Origin private file system to ensure that even their largest files could be performantly worked on. You can do it. Generative AI in Photoshop on the web. And creating PWAs is more accessible than ever. Modern meta frameworks and bundlers, including Next for React, Next for Vue, and SvelteKit for Svelte, as well as Astro and Vite, all have built-in or widely supported extensions for creating PWAs, including zero config options. There are developer tools like Lighthouse that can be used to test if your website meets installation criteria and more, including as part of your CI/CD process. There are libraries like Workbox to help you build and maintain your service workers, allowing you to quickly implement and leverage common caching and serving practices. And there are tools like Bubble Wrap and those powered by it like PWA Builder to simplify the process of bundling your app for distribution in stores. Speaking of stores, Google Play, the Microsoft Store, and Samsung's Galaxy Store all support listing PWAs, letting them take part in the App Store discovery, preview, and review process. Take Boostroid, a Ukrainian-based independent cloud gaming provider, for example. Boostroid lets users stream everything from indie games to high-level AAA games through their PWA, letting anyone play their favorite games regardless of what hardware they have. By improving their web experience and publishing their PWA to Google's Play Store, they found a 60% increase in their year-over-year Chrome OS users, and that Chrome OS playtime increased by 30%. Or Clipchamp, an in-browser video editor that had never been available in an app store before. They saw their PWA installation rates increase by 97% a month in their first 5 months after upgrading to a PWA and listing it in the Chrome OS Play Store, with PWA users having a 9% higher retention rate than standard desktop web users. Their video editor, it also got an overhaul, moving from Knackle to WebAssembly. Clipchamp's success with PWAs isn't unique. On mobile, from a May 2021 case study, Mainline Menswear, a UK-based clothing retailer, saw a 56% increase in conversion rate for their PWA versus their mobile site, along with a 12.5% higher average order value and 243% higher revenue per session. From a June 2021 case study, Bibli, an e-commerce marketplace in Indonesia, found that their PWA generates 10 times more revenue per user than their previous mobile site. They reduced their bounce rate by 42%, and they show an 8 times improvement in mobile conversion rate. And from a May 2021 case study, Orange Polska, SA, a leading telecommunication service in Poland, saw a 52% increase in conversion rate for their PWA versus their previous mobile site, along with 30% faster average loading times and an 18% increase in session length or depth. And on desktop, we're seeing the same thing. From a December 2020 blog post, Kapwing, an online image, video, and GIF editing platform, yes, GIF, saw that within the first 5 weeks of launching their PWA-ified website, the number of people creating videos through their PWA grew 36%. This outpaced overall website growth and indicated to them that retention rate among creators who installed their PWA was higher. And from a December 2020 case study, Corel Corporation's Gravit Designer Pro, a powerful vector design tool that also offers Windows, Mac, and Linux apps, saw that PWA users are 24% more active than any other install type. They account for 31% more repeat users than other platforms and are 2.5 times more likely to purchase Gravit Designer Pro. Over the past 6 years, we've learned a lot about what it takes to build a successful PWA. When they were first introduced, PWAs were about push notifications working offline and being installable on phones. It was about push notifications to make your, there was a push to make your whole website work offline. And there was an app shell model that was encouraged and favored single page apps where refactors were encouraged. But today, we know that any way you want to build your site, be it a single page app or a multi-page app, static site or a dynamic site, are all great options for building your PWA. We've seen that even minimal work, adding a custom offline page in a web app manifest, can go a long way to producing real results without needing to re-architect your whole site. And we've learned that outside of social networks, basically no one likes push notifications. Today, it's no longer a question of if you should build a PWA, it's why aren't you building a PWA? But maybe that's not fair. Sure, making a site installable is now easier than ever, and there are benefits from even that little bit of work. But is that enough? When the web is capable of delivering a particular experience, it can compete. Even with all the advancements we've seen with the Capabilities Project and the growth of PWA adoption, there are still places today where the web can't deliver experiences users and developers want. As we look to the future to fill in these gaps, we've run into a blocker, the web's security model. Because the web aims to be safe and secure by default, its security model needs to be very conservative. Any new capabilities added need to be safe for a casual user to accidentally come across through a URL. At Google, we call this the drive-by web. Drive-by web APIs are generally considered safe if they can be explained in one of two ways. Their power and potential danger can be understood either by the direct action the user is taking, like with web share or web share target or app shortcuts, or a clear and easy to understand permission prompt can be presented that allow users to make an informed choice, like the web Bluetooth and USB APIs or the file system API. Unfortunately, this precludes a number of really important APIs that developers need to deliver the experiences they want. Remember Chrome apps back from slide 11? Well, While they've been deprecated just about everywhere since 2020, they're still supported on Chrome OS. As we've been working with partners to turn down support on Chrome OS for Chrome apps and migrate them to web apps, we found that many of the APIs they need couldn't be made safe for the drive-by web. We needed a more secure environment in order to expose these APIs. A high-trust security model for web applications needs to be thought of differently than the drive-by web. Not only do we need to consider how users perceive the power a web app can have, we need to take into consideration attack vectors that may seem more prevalent to native apps. We ultimately landed on a three-piece requirement for high-trust security model for the web to start exposing some of these APIs. They need to be packaged, isolated, and standalone. What would happen if your server were to become compromised and starts exposing and serving malicious code? Or even worse, what if your DNS becomes compromised? Bad situations like these can become untenable security risks when you're exposing system-level APIs. Because of this, even basic web building blocks, like servers, can no longer be explicitly trusted. To gain access to a new high-trust security model, sites will need to be packaged with all of their resources to run, and they need to be signed into a web bundle, concatenating these resources together with an integrity block, basically a signed key. Doing so allows websites to be securely downloaded in their entirety and their contents to be inspected and verified before installing and running. But bundling code and verifying it before running breaks down if things like storage and permissions aren't separated from the main window. It also doesn't do any good if you can get around this by downloading code at runtime and then running it however you'd like. In order to maintain the trust set up through packaging, websites opting into the higher trust security model need to be isolated too. This means three things: running on a separate protocol, isolated apps instead of HTTP or HTTPS, with a package-specific host, so not your domain, something unique. Isolating it from the drive-by web and other installed apps. You're going to need to declare what permissions you want to use upfront in your web app manifest. And you're going to need to opt into a stricter set of content security policies and cores and co-op headers. These changes aren't just big for developers, though. They're big for users, too. Because apps running with a high-trust security model don't quite install the same and don't quite work the same as normal websites, they're only able to be run in a standalone window. This also reinforces for users that they may be more capable and may get access to system-level APIs like native apps. With this, I've come to start thinking about security and capabilities of web apps kind of on a spectrum. There's the drive-by web. It has the lowest level of trust because it needs to be the most accessible and therefore has the least access to a user's system. Installed web apps get a little more trust and can integrate a little bit deeper into a user's operating system. Then there's this high trust isolated web applications. They act and feel more like native apps and can even get access to deep system integrations and powerful capabilities. Because of this, you can't really easily jump between one of these high trust apps and PWAs or web apps like you can there. When trying to decide where on the spectrum you should be aiming, default to the lowest trust security model that you can, closer to the drive-by web than these new security models. This will give you the greatest reach, reduce the amount of risk you're going to need to manage about the security concerns of your app, and it will be the most flexible for your developers and your users. While we think these high-trust, isolated web applications and the APIs that are enabled with them are important, we also believe that you should only reach for them if you can't deliver your experience otherwise. Because of this, we're taking the same approach here as well. We're only going to deliver APIs to this high-trust environment if we can't make them safe for the open web, or the drive-by web, I'm sorry. But what kind of APIs would need this level of access, this level of security? One of the kinds of apps we've been looking into enabling is virtual desktop infrastructure apps, or VDI applications. And they've got some specific needs that make deploying a fully featured one to the web today kind of difficult. In the world of desktop virtualization, VDIs are somewhat unique. Instead of running a virtual machine locally, VMs are run on a server, and you connect to that server from another device. This can come in the form of a remote desktop, where you've got a window that's a full display of the VM desktop, individual streamed applications, or some combination of the two. And while being lag-free, and you need to be lag-free for video playback that whole time. While the remote desktop situation can be mostly built today on the web, if the server supports WebSockets, but many servers don't, especially older servers. And in providing a seamless streaming app experience or letting users pin apps from their remote session for easy access, and you're going beyond what can be accomplished safely on the web today. A number of APIs are going to be needed to make this a reality, but 3 are ready for you to start testing today. Let's take a look at them. First up is borderless display mode. Imagine you're streaming a Mac app on your Chromebook. The whole window gets streamed, including the app's window title bar. This creates this really annoying experience where you have the streaming app's title bar and then your native OS's title bar. The borderless display mode allows you to remove the OS's title bar, letting apps fully render their own, including specifying areas where the user can drag and soon closing and maximizing and minimizing the window. Why does this need to be a high trust API? Well, spoofing. A blank window with no window controls could be used to spoof anything, a desktop, an app, a website. To mitigate this, not only is this available only in this high trust security application, it requires users accepting window management permissions for the app before it will work, which can be revoked at any time. Next is direct sockets. While WebSockets and WebRTC are great for sustained connections between modern web servers and clients, there are a slew of other devices and servers that just don't work with them. They can't be covered or they can't be updated to being covered. For these, access to low-level socket connections are needed. Direct Sockets API introduces the ability to create TCP servers and connections and UDP socket connections. Why does this need to be a high trust API? Well, both WebSockets and WebRTC are by design highly constrained to prevent abuse. These are not, allowing the same power a native TCP and UDP connection would have. Configuring TCP and UDP connections or explaining why in an easily to digest prompt is really difficult. They have a lot of power. They rely on IP addresses and they rely on ports which most users won't understand. So in order to open these up, they need a high trust security environment. And then finally, there's the controlled frame API. Today, there are 2 main ways of embedding content onto your website. An iframe, which allows you to embed content and communicate between the main website, the parent, and the embedded content, the child, through post message. And fenced frames, which is an upcoming standard to allow you to embed content while maintaining isolation between the parent and the child and explicitly preventing communication. I know that the slide's blank. I'll get there in a second. But VDI apps and many other apps may need something more. Imagine trying to use a video player or hold a virtual meeting through a VM streamed to your desktop. The lag would be terrible. So maybe you'd embed the video instead on top of the screen, but then you wouldn't be logged in. And someone may be able to navigate away from the embedding. All of this means that the current set of tools just doesn't work. Controlled frame allows websites, even secure websites, that otherwise can't be embedded with iframes, to be embedded with what's happening inside of them being controlled or monitored, and then even being able to inject JavaScript and CSS into that page to manipulate it. You can think of them kind of like a web answer to native web views. Why does it need to be a high trust API? Well, it's dangerous. When you have full control over an in-app browser like this, the parent now has access to and can change anything on that website. And it can potentially expose private user data and subject them to fingerprinting or spoofing attacks. Much like direct sockets, only allowing them in these high trust environments helps mitigate most of those issues. So what does it look like? Let's see the demo, right? It'll play. Excellent. To help align user expectations with what these apps are capable of, they're going to get a formal install ceremony, just like native apps. Here you can see me installing a demo app and stepping through the installation wizard. Once it's installed, I can find the app in my app launcher, just like any other installed app. Show my app launcher. There it is. Next, borderless mode. Here you can see me requesting access to it, which asks for permission to manage windows. Once granted, the normal app Chrome is removed. You can designate an area in your web app as a draggable region to move the window around, and we're working on APIs for closing, minimizing, and maximizing the window as well. You'll also see me managing permissions here. App permissions for these apps can be accessed through app permissions just like you would on the rest of your platform. And if you were to revoke permissions, it's instantaneous. Goodbye. Great. Next is direct sockets. Here we can create a demo server ready to receive connections. We can create as many connections to that server as we'd like and send information to it. The server can tell when a new connection has connected or disconnected, and the data is received in a raw unit 8 array bytes, which can be transformed into whatever data you need. Servers can also send data to all connected devices as well. Great. And finally, we have controlled frame. Here you can see me embedding google.com, a site you normally can't embed through iframes. I'm injecting CSS into it as a background color, and I update the site. You can also run JavaScript on the embedded site. Instead of feeling lucky, tell me how you're feeling, and I'll update the button to make it so. I took this video on Valentine's Day, which is why I used a heart. Ta-da! So you can try this yourself. While these standards are in progress, or these proposed standards are in progress, I should say, they are available for you to try and start working with. Double-click to install in borderless display mode are available on Chrome OS Dev version 123 or greater, and direct sockets and controlled frame are available on Chrome Dev version 123 greater on any platform, any desktop platform. You can also download and run the sample code shown here by going to github.com/chromeos/iwa-sync. And if you have feedback about these APIs or questions, feel free to leave them there. I'll monitor that and pass them along to the Eng team. And you can also keep up with me. I'm probably going to be posting a lot about this as we start to roll this out on my various social medias, snugug.com/links. And finally, I want to have a special thanks to these individuals. They gave me all of the information on all of the history going back nearly 20 years on how PWAs came to be. So I appreciate all of their time and effort helping me build this talk. Thank you.